Hi, and welcome to Roboconhelp India Basic Concepts Level 1. We will be talking about basic concepts of robotics in the current level, such that it helps any novice or an amateur who is about to begin in robotics or looking forward to make a robot, and he does not know, or he or she does not know how to begin and how to make a robot. So this video lecture will actually help somebody to do that task. So we'll talk about elements of robotics. Any element of robotics are five basic elements which are comprised together such that it makes a complete robot. It starts with locomotion. Suppose you have to make a robot which performs a certain task. Suppose it has to move from point A and reach point B to pick and place an object. Suppose a ball is placed at point B. The robot goes, picks up the ball, comes back at suppose point C and drops it there. So the same task, if it has to be performed via land, so the method of locomotion can change. And if the same task has to be performed maybe in water, so the same task could be performed in a different way by a different robot. So changing the via media through which one has to maneuver, the kind of locomotion changes for the robot. For different kind of locomotion, you need to have different kind of actuators. Suppose for water, you need to have waterproof motors or something else. And if you have to manipulate certain tasks, suppose in this case we were talking about picking up a ball and placing it somewhere, so you need to have a manipulator which does that task. To give that power to that manipulator, you need to have certain kind of transmission systems, and all these four elements must be controlled together to have a synchronous operation via a control system. Let's talk about locomotion first. In the consecutive lectures or levels when we increase, we'll talk about further elements like actuators, transmission systems, manipulators, and control systems. So let's start with locomotion first. So what is locomotion? As we have already discussed, locomotion means starting a displacement from a starting point to a destination point. And as we have already discussed, that if the change of media is done, then the kind of locomotion changes. Let's take for an example, on a flat cemented road, you will easily opt for a good wheeled robot. And if you have a unstructured environment, you'll have to use a different set of wheels or a different kind of mechanism in your basic robot structure. Or you may also think about changing the wheels or replacing them with legged motion. Legged motion can also be done on a vertical wall, just like in real life you see so many lizards or so many small insects which can walk on walls. If we have a change of media like water, then the robot must be able to swim such that it could perform tasks via locomotion in water. Also, there are other ways where you need to have very slow motion such that only crawling is required. And if the very quick motion has to be required, then flying is the only option. So there are different ways of locomotion which can be used for making a robot. Let's talk about them one by one, and in the current level we'll talk only about wheeled motion, because wheeled motion itself is a huge topic, so we'll touch every topic in detail in consecutive lectures. Let's start with wheeled motion. We'll talk about wheeled motion. So first look at various concepts or designs which generally robots have. We have an example of Dragon Runner, which has 4 wheels and it has a camera fitted on it. And the best part of this robot is that even if it topples upside down, it is still capable to be in operation, because the wheel size is quite big enough than its chassis. The same 4-wheeled robot could be used with a track belt, such that there is no gap between two wheels which are adjacent to each other. If you remove or replace, or maybe not replace, if we remove one wheel out of the four wheels, we are left with three-wheeled operation of a wheeled robot, and where the first wheel, the front wheel, acts like a caster wheel such that it gives direction to the robot. If we remove this first wheel as well, we are left only with two wheels, and this is a good example of a two-wheeled robot which is just made out of some CDs. So it's made out of some waste material, and the PCB which is controlling the whole system acts as a chassis material with this green base. So also, if we remove one more wheel out of these two wheels, we are left with a single-wheeled robot, which is not yet. Uh, it is, yes, until a certain extent people have made it, but a good example in real life would be a balancing of gymnastic on a single wheel when you visit a circus. So let's talk about these wheel configurations in detail. Suppose you have a four-wheeled robot system, and this current diagram shows that the support polygon of the center of gravity of a four-wheeled robot system. Now, if you talk about support polygon, it is actually an imaginary line drawn through all the contact points on the ground which are made by the wheels. Suppose there are four wheels in a robot, so the four wheels actually make four contact points on the ground. If you draw an imaginary line through all these contact points, you end up finding a polygon within which the center of gravity of the robot must lie such that it is capable to perform the task with ease. A good example will be, suppose you are standing straight and without moving your feet, if you try to bend yourself in front to pick up a heavy object, and if you are not moving your wheel, if your feet completely fixed on the ground, and if you extend your body upper torso beyond a certain limit, you will definitely topple. Similarly, if there is a robot whose center of gravity does not fall within these polygons, there are good chances that the robot will topple or it will overturn itself. And second example would be, if you remove the fourth wheel of the robot, you're left with only three-wheel configuration system where you have three contact points on the ground, and if you draw an imaginary line, you will find out that you are left with a triangular polygon, support polygon, within which, if your center of gravity lies, the robot is completely safe to perform any task. But the moment it crosses that line and the center of gravity of the robot is beyond this polygon, there are chances that you will not be able to perform that task and your robot may attempt to failure. If the third wheel in operation is also replaced, you're left with two-wheel system, and this two-wheel system is similar like a straight line which is drawn through only two contact points on the ground. A good example will be a simple two-wheeler bike or a bicycle where the person who's riding that bicycle is balancing its own center of gravity on a single line. The moment that center of gravity goes on left or right of the same center line, there are chances that this bike or a bicycle will topple on sides or fall on sides. So similar concepts applies to the robot if they are made in any of these configurations. Also, if you remove one more wheel, you are left with only a single wheel robot on which there is only one single dot or a single point on ground, contact point. So if that kind of robot has to be made, so your center of gravity has to balance itself such that it always remain in line with that single dot on the ground, which is representing a single contact point of the wheel on the ground. Let's move ahead. There are different kind of wheel configurations. Suppose if we talk about only two wheel configurations, which we discussed earlier in this fourth case with the green base. Suppose we have only a two wheel configuration. This is basically called a differential kind of mechanism where you have two actuators or motors, which are capable to run two wheels separately. Suppose you have to perform maneuvering through a certain media, or you have to take turns. You have to, so there are different ways. If both the wheels, left and the right wheel, are turned together in clockwise and anti-clockwise direction, the same robot can take turns via its center of gravity. It will rotate about its own center of gravity. So that is called coaxial rotation. Coaxial rotation means it is actually rotating about its own axial axis. If that is not to be done, what you can do is you can just move one wheel and keep the other wheel fixed such that it goes and takes a new position. Similarly, in the other way, the red one shows that this wheel on the left side was made stationary, and on the other wheel was made to turn such that it was able to take a new position. If both the wheels are moved together in forward direction, obviously yes, you will move forward, and the same case applies in the backward direction. This other diagrams show that how simple a differential drive mechanism could be if you are able to make a two-wheeled robot. Just by creating a certain time gap between the rotation of the left and the right wheel, you will be able to maneuver or manipulate a simple right or a left turn. Okay, let's talk more about three-wheeled robot and two-wheeled robot. There are three-wheeled robots where, as I told, that the center of gravity must lie between this triangular polygon, and the same case has been displayed over here. Suppose the center of gravity is falling between these the wheels, the front and the rear wheels. The weight distribution between the main drive wheels and the rear drive wheels and the front caster wheels is shown over here. Suppose the same robot has to move down on a ramp. So the center of gravity now is situated actually on the front wheel. So there is less chances of this robot to topple. But the moment the same robot goes on an upward ramp, so the center of gravity is now situated over the rear wheel, causing the main wheels to lose traction, and there are chances that the robot may topple on the rear side. But in the upper case, when the robot was on the downward ramp, the center of gravity was shifted towards the main front caster wheels, so there were chances that the robot would slip in the front. Okay. Let's talk about two-wheeled robot. Two-wheeled robot is something like we have to balance, as I told, your center of gravity on a single line which is connecting the contact points in the ground. Over here, for such cases, you need to have inclination sensors, or in another case, the inclination sensors could be an IR sensor, which could able to sense your inclination with respect to ground. And a good example is, suppose you have to move up a staircase or a ramp yourself, your general tendency would be to bend yourself upper torso in the front. Why? Because you have to balance your center of gravity, which is by default moving towards the back side or the rear side. But when you move up a downward ramp, so the robot leans forward such that it maintains the speed and balance. Similarly, if it has to move down a ramp, it has to move again backwards to maintain speed and balance, such that sufficient torque could be generated to climb up a ramp or climb down the ramp, keeping the weight over the wheels. The main idea is that the center of gravity or the weight of the whole robot should be in line with the wheels, or should be in line with the polygon, or in case a single line which is connecting the contact points in the ground. Here you are seeing different configurations with the wheeled robot. You can have a simple triangular wheel configuration, or a simple four-wheel configuration, or the simple four wheels could be placed at an angular position. The wheels which are being used over here are called omnidirectional wheels. These are easily available in market, and these days it is heavily used in Robocon because people are using these wheels to be placed in their robot. The best part about these wheels are they are able to move in the axial direction as well as in the radial directions. So they do not obstruct any motion in both the directions. We have few tips for people who are looking forward to make a wheeled robot. Just like jamming, generally people have a tendency, they drill a hole in the wheel slightly smaller than the motor shaft and press fit. This idea is good enough because um, you are able to completely fix the wheel on the shaft quite quickly. But as recommended, it should be avoided as much as possible because jamming also makes you unable to replace the wheels in the second time. If you have to replace the wheels again and place another wheel on the same motor shaft, then it becomes tougher to take out the wheel and replace it. Also, you may damage the motor shaft. Instead, the better idea is to use a servo wheel mounting, which is being showed over here in the diagrams. Use the servo horn, drill the hole in it, and use it to mount the wheels on the motor shaft. This becomes easy. Says that you have this is something like you're replacing the mounting every time you have to change wheels with the motor shaft. This becomes quite easy. Okay, uh, sorry. Yeah, so wheels, we have few tips like bigger wheels let your robot move at faster rate rather than smaller wheels for slower speed. Why? Big wheels have less torque to carry heavy payloads, and fine position control is hard to achieve because the diameter or the perimeter of a big wheel is larger than a smaller wheel. So in a single rotation, when the big wheel follows in the ground, the amount of distance it covers is quite huge or large with respect to a smaller wheel, which performs or which covers a lesser distance in single rotation. So when you are using a bigger wheel, fine position control is hard to achieve. Sometimes sensor cannot keep with the fast changing position of the wheels. Suppose you have to make a robot for racing operations, so you have obviously know that when you use a bigger wheel, it becomes easier for you to win that race. But obviously keep yourself limited to the norms of the rules of the competition, because competitions may limit you to choose the good wheels for a good operation. Let's talk about wheel basics. We'll talk about wheel diameter first. First thing you have to decide on motors is finding the torque and velocity. Large diameter wheels gives low torque and high velocity. If you have strong motors, then you can use large diameter wheels. If your motors are weak, then small diameter wheels will work. A dumb mistake which people can do is that they can take wheel diameter close or closer to or less than the diameter of the motor. Suppose you are taking the diameter of the wheel which is almost close or lesser than the diameter of the motor. It is obviously gonna not work. Keep the track of ground clearance in your mind whenever you are making your wheel robot. So the wheel diameter must be kept in your mind while making a wheel robot. Second is wheel texture. The texture of the wheel is dependent upon the terrain. So if your wheels are smooth enough, thus no friction, the wheels will keep skidding while accelerating and braking. Consider wear and tear on the wheels as well when you're making a wheel robot. The wheel width or the thickness of the wheel, don't make too wide wheels. It increases the resistance for the wheel to rotate on surface. If you could see, a good example is the racing bikes, racing bicycles. They're using a very thin tire in the bicycles because the moment you increase the thickness of the tire or the wheel, it actually increases the resistance to rotate on the surface. Wheel center hole diameter, the place where you put the motor shaft output shaft. It is the place where the wheel center hole is there. know the exact length and diameter of the output shaft. If you do not know that, obviously you will end up putting up the wheel shaft, maybe not placing it correctly, or completely passing through the hole of the center of the wheel. Sometimes it happens that the wheel hole is made properly, but the shaft does not enter the hole properly, or it goes only a certain distance. It does not cross the complete thickness of the wheel. So keep these tips in mind while you are making your wheel robot. So this comes to the end of the Basic Robotics 1. Look for level 2 to learn more. Thank you.